What if galaxies don't need curved space or dark matter to spin the way they do? In quantum physics theory, orbital interaction comes from celestial anchors syncing with a flat modular grid. Today I am applying the grid coupling force to a real galaxy's rotation curve, start to finish, in 3 steps. Hook locked, cool. The idea? Anchors, stars, gas clumps, the bulge locked to the grid via Higgs scale mass, mh. Lensing and gravity show up as tiny vibration waves from those anchors rippling across the grid. No curved space-time, no time mixing, just alignment and flux. Here's the plan. Step 1. Build the grid map. I pick a galaxy, say NGC 3198, because its rotation curve is classic and clean. I slice it into rings. For each ring, I estimate the anchor mass locked to the grid, MHR, and I estimate the local grid flux term, how fast new modules sweep that ring, .gr. Practically, I pull stellar mass from infrared light. I pull gas mass from 21 cm maps. Then I convert to Higgs scale mass by applying the theory's celestial scale coupling. Then I assign a synchronization factor, lambda r, from 0 to 1 that captures phase locking. I also compute omega r, the ring's angular phase relative to the grid. Step 2. Compute the grid coupling force. The working relation starts with mhr times lambda r, multiplied by the sweep rate, dr dt or .gr, and include omega r, giving fgr jar mhr lambda r .gr omega r. Think of it as a torque-like push. The expanding modular grid applies to locked anchors. I convert that force per unit mass into an effective tangential acceleration, agr, then into velocity, v model r, SQRTR, AEFFR. AEF can include baryonic centripetal term plus the grid term, but here the grid term dominates. Step 3. Fit and test. I tune only grid native parameters, lambda r profiles, and an overall .g normalization consistent with the expanse's expansion rate. No hidden halos. I compare V model r to the observed rotation curve V OBSR from HI data. I track residuals and look for systematic phase drifts, flat tails, rising outskirts, inner dips. So what do I expect? If the grid drives rotation, V model should flatten naturally once lambda r settles and .g stays non-zero. Warps and bars should appear as local phase shifts in omega r, nudging the curve up or down. Galaxies with higher synchronization, clean spirals, tight bars should need smaller lambda gradients. Quick mini run through. For NGC 3198, I assign MHR from its stellar plus gas profile. I start lambda r near 0.7 in the inner 5 kiloparsecs, taper to 0.5, 0.6 by 20 kiloparsecs. I set a global .g tied to the observed expansion of the grid, constant across the disk first pass. I let omega r capture the bar phase if present, otherwise near aligned. I compute FRG, convert to AG, get V model, and stack it on the data. If the outer curve is too high, I slightly reduce lambda in the outskirts. If the inner curve is too low, I bump omega toward tighter alignment there. Validation checklists, cross-galaxy scaling. Does one .g work for multiple galaxies? Phase lensing tie-in. Do lensing asymmetries line up with predicted omega shifts? Time stability. Does a slow drift in .g predict secular evolution we can test? Bottom line, with just mh, lambda, .g, and omega, I can attempt a flat curve. No dark matter, no curved space-time. Want me to demo this on your favorite galaxy? Drop the name, I'll run the grid. Ever notice how galaxies spin in a way that doesn't quite add up in standard physics? That weirdness gets explained by dark matter, huge invisible halos adding extra gravity so stars on the edge keep up with stars near the center. Solid model, tons of evidence backs it. But let me pitch a different lens. Planet anchorage and dark rotation in a grid-based universe. Instead of empty space as a featureless stage, imagine a hidden lattice, an underlying architecture. Bodies don't just coast on curved space-time, they couple to the grid. Think of it like traction instead of drift. Anchorage says orbits and spins aren't only leftovers from formation. They're actively stabilized by grid coupling forces, call them graviton link effects, giving planets a reference frame to push against. So when a galaxy turns, the flat rotation curve isn't from a shapeless halo, it's from a structured handshake with the grid that keeps disk velocities coherent. Where does the Higgs fit? In standard physics, the Higgs field gives particles mass. Here, mass does more than weigh things down. It sets a mass-size ratio that decides how an object floats in a negative energy scaffold. Dense and compact, it bites harder into the grid. Fluffier, it skims. This isn't mainstream. In general relativity, gravity is space-time curvature, and there's no confirmed cosmic mesh anchoring planets. Orbital motion comes from initial angular momentum and gravity's pull, not a tether to the vacuum. There are fringe ideas. Gravitational action points offset mass centers, but they sit outside consensus. So what's the point of anchorage? It reframes dark rotation as permission, not pressure. Motion allowed by coupling, not demanded by extra mass. If true, stability comes from structure in the void. If not, dark matter still wins on the scoreboard. Either way, asking the question sharpens the science. Does the universe pull us, or does it also hold us? I'm curious which story the data will let stand.